G'day, welcome to the first lecture for week 11. In this first lecture, we're just going to talk about the first law of thermodynamics. It's not going to be a huge topic, but it's quite an important one, so we'll just take our time to make sure we really grasp the fundamentals behind this idea. As usual, I'll jump over to the slideshow. Because it's quite short, there'll just be two videos. This first one, we will talk through all the theory, and then a second short video where I'll just discuss a couple of problems, nothing too strenuous in this first topic. So the first law of thermodynamics. Outcomes for this topic are to be able to define heat, energy, and work. We've met all of these terms before, but we just really want to talk about them in the contexts of these thermodynamic problems. State and explain the first law of thermodynamics, and be able to consider simple systems and apply the first law of thermodynamics. So firstly, as we said, we want to understand this distinction between heat, energy, and work. We've met all these terms before. We know they're all energy. They all have the same units, SI units being joules. They're all some form of the same thing. So what is the difference here? We've already talked about the difference between work and energy. Energy is something that an object has. Work is the application of energy to an object to change something about it, whether it's changing its kinetic energy or its potential energy. It changes part of the energy within the object or energy that the object has through mechanical means. So that is work. Work is the transfer of energy through a mechanical process. Heat, as we've already met, is the transfer of energy through a difference in temperature. So if one object is hotter than another, some of that heat energy, that thermal energy, the internal energy of the object, that heat flows from one object to the other, from the hot object to the colder object. So remember that it's only heat as it's flowing. Heat is while it's flowing. When it's in the object, then it's internal energy or thermal energy. Only as it's leaving the object, as it leaves to go into the colder object, do we call it heat. While it's inside the object, it is not heat at all. So what happens to internal energy? We already talked about this as well. If we apply heat to a system, then the internal energy of a system must increase. If heat is lost from a system, then the internal energy of the system must decrease. Now by convention, we call heat positive for this gain. So if heat applied to a system is positive, and the internal energy is going up, then they are positively correlated. So we get the change in internal energy is equal to Q. If we have heat lost, it's a negative Q, and so delta E int would be negative, so it still works that way. For work, we've got to bring in this idea of being able to change the internal energy by work. Now, we already know that can happen because we talked about the mechanical equivalence of heat, where we looked at James Prescott Joule and his little paddle wheel, and he heated up some water by applying work. So we know that work can relate to internal energy, but the convention here is actually the opposite of what most people would expect, and that is if we do work on a system, so that is we're giving some energy to the system, we're doing work on it, we actually call that negative. We call that negative work, and if we have work being done by the system onto, so work energy from the system, then the internal energy of the system must decrease. So that makes perfect sense, but as I said, we have this convention of doing the signs the other way around. So the work done on a system is negative, the work done by a system is positive, but because work done by a system, which we've said is positive, decreases the internal energy, our relationship is actually the change in internal energy is negative of the work. The only reason we have that convention is because historically this was often used for engines. So for example, a steam engine, and what they cared about was how much heat they had to put into the engine versus how much work they got out of it. So it was purely a result of the preference of what they were considering when they used this equation. So in that sense, we've got Q being positive, but W being negative. Just thinking about the opposite ways. So heat into the system is positive, work out of the system is positive. And that brings us to the first law of thermodynamics. It's just combining those two. That's all we do. We've got the relationship between internal energy and heat and internal energy and work. So if we put them both together, Then we have the first law of thermodynamics. So what you can see is that if you have heat and work both happening with a system, either to or from, then the internal energy is going to change based on both of those two quantities, the heat and the work. So it's perfectly possible that you put heat into a system, but that system also does some work, and so it uses up that energy, and it ends up not actually having a change in internal energy. So there's still heat flowing in and work flowing out, work being done by the system, but overall there's no change in internal energy. So that's all the first law of thermodynamics is telling us. It's just another form of the law of conservation of energy. We've seen this come through in multiple different ways, in multiple different scenarios. And if you continue on with your study of physics, you'll see it in many more different scenarios. But it is just the conservation of energy. Energy can't be created or destroyed, it has to be transferred. So if we've got a system and there's energy coming in, then it either has to increase the internal energy or there has to be some work going out. Those are really the only two options. And as I've put as a little note there, if you haven't already figured it out, a lot of physics is simply figuring out where energy goes. Right? That's our job. That's what we're doing when we think about physics. A lot of the time, these systems, we're just doing energy conservation or trying to figure out where it's moving. We already met the idea of open and closed systems. However, in thermodynamics, it's actually beneficial to further distinguish these systems. So we had previously, you may have met an open system being one where mass and energy can exchange with the environment or with other things. Then we had a closed system that was it can't. But now it's useful to actually think about a distinction between the mass and the energy transfer. So what we do is we bring in another term. We bring in the term isolated, and that becomes our new extreme for the closed. So a system that can't exchange any mass or any energy with the outside world, with any environment, is isolated. So that means that the energy in the system is going to be conserved and the mass in the system is going to be conserved. For a closed system, we now actually loosen the definition a little bit. So it's still got mass conservation, can't exchange any mass with the environment, but it can now exchange energy. So a closed system in thermodynamics is just saying that we don't have any mass transfer. There's no mass going in or out of our system, just energy. Whereas open is one that can gain or lose matter and exchange energy. So it can have both transfer of matter and of energy. So that's a new definition. I realize it can be a little annoying, a little frustrating that we've said open and closed before, and now we're saying, oh, well, actually closed now means something different, and let's bring in a new term, isolated, which kind of means the same thing as what we used to mean by closed. So it does get a little bit confusing there potentially, but hopefully by just pointing it out, talking about it for a moment, you'll get that concept quite happily. So it just depends what kind of science you're looking at. Are you looking at a mechanical system, or are you looking at a thermodynamical system? And then what do we mean by open and closed in each relevant scenario? Again, this is one of the points where I often do a little bit of a sidetrack and talk about language for a moment, just because we have now got this new definition of open and closed compared to what you might be familiar with or how you might have been thinking about it. And even as recent as last week when we were doing calorimetry, I was talking about open and closed, and I was using the old definitions because we hadn't taught you these ones yet. And so it can get very confusing, and it's a reminder to always look at the words that you're given and look at the scenario that you're describing and use that context to figure out what we actually mean. If we describe a system and we say that we're giving it some heat from an external source, and then we say it's a closed system, then obviously we're talking about this definition of closed. You don't even need to know the word closed in relation to energy, because we've said it's getting energy. So if it's definitely getting energy from an external source, you don't need to remember whether closed means it can or can't get energy, because we've just told you in the question it is getting energy. So by being able to look at a scenario and figure out what the words mean, you're going to be in a far better situation than if you just memorize a bunch of definitions and then just apply them without thinking. That's never going to end up well. So that's my little sidetrack, just talking about language. Considering systems, you always want to be able to think about a system, look at it and say, what do I expect to happen? What's happening? Where's the energy flowing? Where's the work being done? What's going on here? Do not rely on the just mathematics approach. I realize this is what a lot of people are taught right throughout high school, and even in some courses at university. You just find some numbers, find the equation that has those things in it, chuck them into the equation and get a result out. And plenty of the time that will work, but plenty of the time it won't as well. And using that just mathematics approach will never be reliable in the long term. So what you need to do is actually be able to think about the physics of the situation. So before you do any of the number crunching, before you do any of the equations, you should always be stopping, thinking about the system, doing whatever you need to do some diagrams, just sit there and think about it for a moment, whatever you want, but try and figure out what the system is doing, and then find the equations, find the values, and do some calculations. And that way, once you get to your final result and you get a number out, you can look back at your thought process beforehand and say, does this result make sense? Without doing that thought process at the start, you have nothing to compare that result to in terms of what you expected, and you don't really know if you've done it correctly or not. So it's just a good reminder, always think about the system before you just plug some numbers in. So in that vein, let's think about a couple of systems. The first one, you've got two objects and you're rubbing them together. It can be any two objects, but if you've got your two hands in front of you, they are pretty easy objects to experiment with. So if you rub them together, just rub your hands together, they will warm up. You don't even have to rub them very hard or fast. You will feel them warm up. Right? How do we interpret this in terms of the first law of thermodynamics? So what's going on? So remember, the first law is just relating internal energy to heat and work, and we want to know what's going on here. We're not heating our hands, so our Q should be 0. We've got no heat. I'm not holding a flame to my hands to heat them up. They are getting warmer, but I'm not giving them heat. I'm not applying energy through a temperature differential. I am doing work on them. Right, so Q will be W. We've got no heat, but I am doing work. Right? I'm using my my muscles to convert other. We don't care about all the biological processes, but I'm converting other energy forms into physical motion. So I'm doing work by forcing my hands to rub against each other. So work is being done on the system. I'm doing work on my hands. My arms are doing work on my hands. My hands are rubbing together. So W is going to be negative, work on the system. So that means we've got energy going into the system in terms of work. So remember the convention that Q, heat into a system, is positive, but work by a system is positive, so that would be negative. But it actually doesn't matter at this point whether we're talking positive or negative. The important bit was not that I said negative W, it was that I said I've got work putting energy into the system. Whether we define that as positive or negative, that's just convention. Even if you do it the other way around, it doesn't matter. What matters is that we realize we've got energy going into the system by work. So we've got energy in by work, we've got no change from heat. That means that we must have energy ending up in our system. We must have internal energy being increased. And of course, that's what we experience because we can feel our hands get warmer. And temperature is a function of internal energy, or it's part of internal energy. Remember, it's just the translational kinetic energy. So by rubbing my hands together, I'm applying work, I'm putting energy into the system, which consists of my two hands. And that energy is becoming internal energy, and part of that is going to be temperature, going to be translational kinetic energy. So that's what the first law of thermodynamics is telling us. It's just what we would have already expected. If we put some work into the system, in this case through work, then we'll see an increase in internal energy. In this case, the temperature of my hands rises. So I do have a slide that says that same thing, but as I've said, before you do numbers and define positives and negatives, just understanding which way the energy is going, where it's going, is far more important. Also, a little note at the bottom that this is a closed system. There's no matter exchanging from my hands to the environment, or from my hands to each other, or from my arms doing the work to my hands, although in reality, obviously, there's blood flow and other things, but that's beyond what we're considering. So there's no mass change, but there is energy change because the work is coming from outside the system. The work is coming from outside my two hands. The next scenario to consider is lifting a mass. So we've met a little container like this before with a movable seal when we talked about the ideal gas laws. So this container is full of gas. This blue shaded bit is gas. We've got a movable seal on top of it, and we place a mass on top of that. So we've got this mass resting on the gas. As we heat the gas up, the mass will move upwards. Now, before we even get into the first law of thermodynamics, just think a moment about the ideal gas laws. Remember that this is essentially a constant pressure problem. It's not atmospheric pressure because we've added this mass. So this mass and the area of this movable seal will be adding to atmospheric pressure. So the gas inside here is at higher than atmospheric by whatever pressure is being added by this mass. So force of the weight of the mass, weight force of the mass over the area of the seal. That's how much we've increased our pressure in the gas by. But regardless, that stays the same throughout this whole motion. As it moves upwards, the pressure that the gas is at has to stay the same. So in our ideal gas equation, PV equals nRT, we're saying that pressure is constant, volume and temperature are changing, but N is constant as well. So that means that as the temperature increases, then the volume is going to increase. The volume increase here is only through the upwards motion of this movable seal. So therefore the mass is going upwards. So what we're talking about, you should hopefully have already not even really had to think about and knew from the ideal gas law discussions exactly what would happen. So the increase in temperature will result in a linear increase in volume. So the mass goes up. That means we're doing work on it because we're doing work against gravity. Right? We're increasing its potential energy, even if it moves up really slowly, so it never really gains any tangible kinetic energy, right? If it's actually moving really slowly, even if we do that, it's still sorry about the mouse there. It's still gaining potential energy, so we are doing work on it. So how do we interpret this in terms of the first law? I say we are doing work on it. Work is being done on the mass. So how do we interpret that? Well, in this case, we definitely do have heat being applied. We've got a burner, a flame, some kind of heat source that is applying heat to the gas. So we have Q being positive because the system is receiving heat energy. This time, the gas, our system is the gas is doing work on something else. Work is being done by the gas on, in this case, the mass being lifted up. So we've got work being done by the gas. So remember that if it's being done by, that makes it positive, but more importantly, it means that energy is leaving the system. So we've got energy coming in through heat flow and out through the pushing upwards of the mass. What does that mean for our internal energy? Well, it depends on which one of those has a bigger magnitude. If you put in more energy in the heat than the system is using to do work, then that means that the internal energy of the system will be increasing. And in this case, because it's a gas, there's no phase change or anything, that internal energy increase is going to be an increase in temperature. But if the work being done by the gas was more than the energy that you're supplying it through the heat, that would mean that the internal energy is actually decreasing because it's sending out more energy than it's getting in. That's not a common result here. It would need a special system and a special preset initial scenario for that to work. So the general solution is going to be that the heat going in is more than the work being done by the system, so the internal energy of the system would increase. The gas would heat up. We've met state functions already. We're now going to talk about them again for no real definite purpose. I'm not going to then immediately apply them to everything, just a reminder of this concept. Here we're calling them state variables, but they're the same as what we met earlier, which was state functions. And that's the idea that if you took a freeze frame of your system and looked at everything in the system, if you could freeze it and go through and measure the mass, the velocity, and everything about every particle, then you would know some things about the system. You would know things like the internal energy, the pressure, volume, temperature, mass, and how many particles there are. Those are all state variables. Work and heat, though, are not state variables, because if you freeze frame it, if there's no energy transfer going on, then that means there's no work and there's no heat occurring. Right? In any one instant, work and heat are zero. They require flow of energy, movement of energy, which means they have to occur over time. So you can't freeze frame it and see work and heat. And more importantly, there's no history in our system. If you've got a bucket of room temperature water, it doesn't care if it started as ice water and warmed up to room temperature, or if it started as really hot water and cooled down to room temperature water. Once you've got two identical room temperature buckets of water, that history is irrelevant, right? The state functions, the state variables, they tell you all about the system, and they don't care about the history because the system doesn't care about its history, right? So that's, again, just a little definition. I'm not going to immediately apply that to anything, but it's just a useful reminder to keep these sorts of things in mind, to be able to identify state variables, i.e. things, properties of the system, versus things that aren't state variables or state functions, things that are moving, things that are moving in and out of the system, but don't affect the actual properties. No, they do affect it, but anyway, you get what I mean, right? It's just important to keep in mind this distinction between a property of the system, when you freeze frame it, something that it has, versus something that's being done to or done by it. It's just a slight distinction, and it's just useful to keep that in mind. The first law that we've talked about a change in internal energy over some definite time interval. We've said, okay, well, it's over this period of time, we've applied this much heat and it's done this much work, and we've seen this resulting change in internal energy. That's fine. It's kind of, it's just a big picture version of the law. Sometimes you want to be able to look at an instantaneous change. So you want to say, over an infinitesimal change in time, what happens to our internal energy? What's our infinitesimal change in energy, and how does that relate to our infinitesimal change in heat, or amount of heat flow and amount of work done? And so that's just a useful differential form if you get into the more complex systems where things are changing in non-constant ways, right? So it's kind of like we saw when we write back to mechanics, where we, kinematics even, where we talked about constant velocity versus instantaneous velocity. It's the same thing here. We've got a total change in internal energy. So if you think about some time interval and it changes by delta E int, then you can figure out the average change in internal energy over time. But if you want to know what's actually happening, if it's not a constant change in internal energy, then you can actually look at the differential form and figure out the instantaneous change in energy at any point in time over the system. And finally, we've said that the internal energy changes with heat and work, but we've also said that it's just conservation of energy. So what happens if we've got other kinds of energy to consider? What happens if we have kinetic or potential energies involved in our system? Well, because it's conservation of energy, everything's already energy terms, we can just add them in. If we've got kinetic energy or potential energy or internal energy changing, any of those three things changing, then we must have either heat or work on the right-hand side, right? We have to have this system balancing. So we've got all five of these terms. The important thing to note here is that the three terms on the left, the change in kinetic, potential, or internal energies, those are energy within the system or that the object possesses in some way. The heat and the work are only referring to heat, to energy going in or out of the system. So it's the transfer of energy. So it makes perfect sense. If you've got a system and it's got some amount of energy inside it, the only way that amount of energy inside it can change is if you put energy in or take energy out. So that's all this equation is saying. We now, though, by including kinetic and potential energy, we have the ability to have energy transfer between kinetic to internal or potential to kinetic or things like that. So it actually encompasses everything, right? All those different possible changes of energy. So that's the first law of thermodynamics in full. And it is useful. You do need to know this one, how to apply this. But because it's just bringing in some of that mechanics stuff that we already know, there shouldn't really be any great challenge. If you understand the first law as we talked about it just before, without the kinetic and potential, this shouldn't be any great challenge to incorporate those. So that's the theory content for this lecture. We've got the review on the slides there as usual, so read through that, make sure you're happy with that. And there will be a short video coming up shortly for just a couple of questions relating to this content.